Thank you for the introduction, and I'm excited to be here today and to hear your questions. So please feel free to interrupt me throughout the presentation. Kind of a quick overview of what I'm going to cover. First, I'm going to talk about manufacturing, kind of how it is and where it's going at a kind of a large scale. And then I have some demo material to walk through for kind of an application of where this technology is today. And some customer use case stories to kind of describe how this technology is being used, so you can kind of imagine kind of where we go from today into the future. Okay, so my name is Anna Shidletsky. I'm a mechanical engineer by training. My first job out of school was actually at Apple as a product design engineer. So I worked on designing mechanical components for 3 different iPods, and then I led system product design for Apple Watch Series 1. Product design at Apple is a combination of not only designing the components that go in the product, I call that like packing the suitcase, where the suitcase is the product, but it's also going to the manufacturing line in China often and finding and fixing issues on the first manufacturing line. So we own the whole process from developing the parts that are going to go in the product all the way to one mass production line running at mass production yields and mass production speed. And then there are other people who take that and turn that into many lines, but responsible for demonstrating it's possible to build a product at volume on one line. And as part of that, I spent many days in China, because that's where my work was, trying to find and fix issues on the line so that the product could be ready to go into mass volume. As you know, Apple ships all its products in mass volume. And originally I thought that that was really around searching for perfection, because if you're going to build millions a day of something and you have a 5% failure rate, that is a really large bone pile of units that would fail. So it must be perfect, right? And what I found when I went and learned about manufacturing is actually, no, there's like 5% yield loss. And what you do as an engineer is try to figure out either how to recoup that yield loss, how to reduce it by improving the design, improving the process, improving the product. And as part of that, there's kind of this ongoing shift, even in the period of time, I was at Apple for 6 years before I left to start Instrumental, where there's this shift happening where manual operators on the line, their attitudes were changing. There were fewer and fewer of them. They seemed to have more and more power over the manufacturer. And they started being replaced with machines. And so there were ultimately, while there were higher and higher volumes that were being built, and so more lines with more people, there were also less people on each line because those people were being replaced by automation. And so while it may not come as a surprise to this group, but automation is very much being embraced in Asia as a way for China to maintain its leadership role in manufacturing, and especially consumer electronics and electronics manufacturing in the world, which is a sentiment that the US hasn't really embraced from an automation standpoint. So this revolution is a little bit quiet because it hasn't really left China in terms of this understanding there's actually a change happening. And in China, automation is old news. And even in the US, people think that most products are made by machines because they've seen YouTube videos that look like this. The interesting thing about this, though, is that this is only 15% of the line, and the rest of the line is still manual. There's still people there. Internal assembly is done by people. The subcomponents is done by people. Many of those subcomponents could be built in other parts of the world and shipped in fully, like assembled, and then the final like insertion into the car might happen here locally for cars that are being made here. And so I think people have a little bit of a skewed perception of how far along automation is in manufacturing. It's not totally there yet. And actually, most lines still look like this, where there are 110 meters of people shoulder to shoulder every 6 meters. And so that's kind of an interesting thing that's a little different than most people think. But automation is required to be globally competitive because it's coming. The machines are now getting better than humans are. For the longest time, humans were the cheapest option, and you can retrain them in minutes to do a different task. It's very difficult to do that with a machine. A machine requires an engineer to retrain it, and it takes days and lots of units to do so. But essentially, that the large numbers of people that are being used to assemble consumer electronic products, even in China, won't be there for very much longer. And the key idea is there's actually two forces at play. One is there aren't enough people that want to do these jobs anymore, and so the wages are going up not because the job sucks, which it does suck. It is a very repetitive job, but also there's just fewer and fewer people who want to do it or who are available to do it. And so if you're ramping products like iPhone X or iPhone 8 or Samsung Galaxy Note 8, these are products that they ramp to volumes of 1 million per day. You need many people building these products on these lines, and those people need to be bussed in. I've sat in meetings at Apple where they're talking about where the beds are and how far away they are from the line, and like, oh, these beds are 45 minutes from the line. Like, these are all factors that are being discussed of how we're going to get enough people to do these jobs. And so actually the motivating factor is to replace people with machines because the people aren't there. And it's not because machines are cheaper. It's because the people don't show up. Turnover in China is also a big problem. You can have 15% week over week turnover. And Chinese New Year Golden Week, it could be 50%. So imagine you train up your staff and you're trying to ramp your product. Chinese New Year happens, bam, you have all new staff. And you got to train them again. And this is the reality. But if you have machines, that doesn't happen. So there's a lot of motivation here. And the Chinese government is really smart. They've realized that this is a key innovation advantage and that they want to be leaders here. And so the government is actually subsidizing a lot of development in automation in the manufacturing space. The US obviously hasn't caught on that that's an important thing to invest in because we're trying to do the opposite. But this is something that very much is ongoing. And so automation I view as kind of a foregone conclusion. It hasn't fully happened yet, but like the war has been lost between human and machine, and it's just now like still kind of working its way through the factories. So as people are replaced with machines, there'll be kind of a result and an opportunity. So before humans, we have really limited outputs, right? Like we're great because we have like eyes that work and fine motor skills, and that makes us great automatons to do tasks. But we have really slow outputs. We can speak, we can type, we can handwrite. Whereas machines can output at the speed of light, and you can transmit information very fast, and machines can talk to each other very fast. And so you have opportunity to transmit data that was not available before because you have machines doing the tasks. And so instead of an operator who is, putting part A into part B and pressing and putting, pushing buttons, sticking a label, you now have a machine doing this task, and the machine has the force it pressed at, the profile of how it moved, what the resultant gaps were, what the initial part size was, what this part size was, all that data. And that data is really valuable, and it wasn't available before, and there aren't software systems that have been built yet to actually accommodate that data. And so that creates an opportunity, because if you do have a software system that can aggregate and do smart things with that data, you can actually create lines that continuously improve themselves. So what that looks like, you've got a line, you've got robots down the line, no people, like this thing can run in the dark, the lights out factory. All of those robots communicate to a centralized server or system or intelligence system. And all that data comes in. There is a system there that's doing smart things with the data and can actually find useful information. And that's called manufacturing intelligence. So this is where that centralized brain takes in the data, uses machine learning, artificial intelligence, big data analytics to come up with not just dashboards of the data, but actual insights that this is correlated to this. And if we move this knob, we expect this result because we've seen that perturbation in the system before. So this enables you to improve the yield of the performance of a specific step by making a change upstream or many changes upstream. And these can be quite complicated. Today, humans do this. This is what I used to do, and we're really bad at it because our heads are full of meat, and we can't keep all of the data in our minds, and we have to do a guess and check, like, okay, hypothesis. Maybe the antenna performance is bad because this is happening. I'm going to go check to see if that's the case. Whereas a machine that's processing all the data has already looked for all the brute force that has already done all the brute force calculations looking for correlation and has probably presented me as a human with a bunch of different ideas of what I could do, and now I can actually see in the data what the results might be from previous perturbations. So there's a lot of opportunity for building software that will essentially harness all this data that's newly available or is becoming available. Any questions so far? Yeah.
So what you talk about is very, I guess it's same as the Industry 4.0 concept, right?
Yeah, so I really hate buzzwords because I think they actually make things more confusing than clear. But yes, the concept of Industry 4.0 is the same idea. You apply sensors to the line, and then from those sensors you can get useful data and useful insights, and then do something like create a closed loop control. However, like this has been done for a very long time in the semiconductor industry. It's called advanced process control. It's been in place for at least 20 years. It's the reason any chips can be made at all. So like this whole idea of Industry 4.0 being like super new, it's only because we've started to automate parts of it, whereas in the past it was done by people, and then smart people like yourselves, engineers. So let's talk about an example. So in this example, hypothetically, we're building some new phone. Okay, so we're a product company, we're going to build this phone. And a phone needs to have many functions to work, but one of the key functions it needs to have is it needs to have an antenna that works, because it's not a phone if it doesn't have an antenna. It doesn't have a camera in order to be a phone, but it does need an antenna. And so when you're building a phone, you essentially, or you're going to assemble it, you have that final phone, and you're going to put that into a test station. This is industry standard. Okay, we're going to make sure that the antenna works, because if the antenna doesn't work, we're not going to ship the product because it's not a phone. So you put it in this test station. Essentially they're anechoic chambers. They look like little college mini fridges. You put it inside, click a button. Some smart engineer has written a test script to make sure that the antenna is good, and then some data is produced. And that data is in a parametric format for an antenna test. It actually kind of looks like that, which I'm not an antenna engineer, so I don't know what that is called, but that is the graph that is output. And that graph in there is information about whether the antenna meets the specification and is okay to ship. And so there is software that's written to say, oh, okay, it looks like this. That means it's pass or it's fail. And today, that pass-fail result is pushed to the line. So the operator who put the unit in the mini fridge now knows, okay, this is a pass, so I put this back on the line and it goes down the line, and hopefully the rest of the test pass and we can ship this unit. And if it's fail, I put it over here in the not good area, and someone else will come and retest it. In the process, the test station has also collected that graph. That graph is super important because it shows why it was pass or fail, if it was marginal pass, marginal fail, what is the shape. The indication of the shape could help an engineer like me, who's responsible for making sure this thing works, to come and actually fix it if it's broken. So if I have a bunch of them that fail and they fail in the same way, I know I'm looking for one root cause and they're all similar. And that's really helpful for me. That parametric data is super valuable for an engineer. That data is not stored by the factory. Today it's kind of put into, I call it a filing cabinet, because that's essentially what it is. The company who's building the phone, we're the phone company. So our company has set up a server in the factory to put that data on it. And we essentially just shove some of that parametric data, maybe not all of it, maybe just pieces of it, to the filing cabinet. And if we have a problem with this unit, we can go dig through there and we'll have something to do failure analysis with. And what's happening now is that there's kind of been this, for the last couple of years, this idea of manufacturing analytics, which is this emerging field where the idea is, let's take the data from the test station and put it on a dashboard. Because if we put it on a dashboard, then engineers don't have to go to the line to see what's happening on the test station. They can see it from their desks. And if they can see it from their desks, they can monitor it better, and maybe they can do some better analysis. But all we're doing is we're taking the same data that's on the machine and we're putting it at someone's desk. So there's like a transfer that's happening. But this is useful and this adds value, and there are companies that have found significant yield improvements by using manufacturing analytics. So this is actually, it sounds very simple and not that novel, but is still very valuable. And so that is something that's kind of happening, but this hasn't really come to the contract manufacturers of China. So like the top 3 tier 1s and then into the tier 2s, not really using this type of technology. What they're really doing is they have these old databases that are not relational databases, and they make daily reports in Excel. And then they send those Excel spreadsheets out to the engineers, and the Excel spreadsheets have conditional formatting so that certain boxes turn red, and the engineers don't read the entire thing except for the boxes that are red. And sometimes they make mistakes in the formatting, so there's boxes that aren't red that should be, and nobody finds them. And this is the way that engineering is done at the top contract manufacturers and the top brands that are building there. And this manufacturing analytics thing is just like something that they haven't yet invested in or seen value in yet. So there's kind of been this interesting thing to watch what technologies have been adopted. And so we are the phone company, though. We want the dashboard if that's going to make our phone better, but how do we actually make it better? This dashboard only tells me I have a problem. It doesn't tell me what to do about it. I still have to hire lots of engineers. They still spend lots of time. They still probably have to take that unit apart. How do we make the phone better? And so that's what manufacturing intelligence is about. It's about getting rid of the filing cabinet and even maybe getting rid of the manufacturing analytics dashboard, because the dashboard is just really moving data. It's not actually providing additional insight. And so that's kind of what we're trying to do, Instrumental's trying to do as a company, is build manufacturing intelligence. And so what that is, instead of taking just a piece of the data, take all of the data, everything that test station generates, and put that in a database. And then that database runs algorithms. So instead of a filing cabinet, it's like a filing cabinet with gremlins inside that are doing smart things with your data while you're not watching. And then when they find things, they will push improvements back to the line. So whether that like backward improvement goes to a person who then goes over to a station and makes a change, that's going to be the first step. Or it pushes that improvement directly to the machine that's doing the operation and no person's involved at all. And then what it can also do is it can provide forward reporting to the engineers to say like, oh, these were the defects that were found and the insights we found, and we please approve, we'd like to change this and this should get this yield result, push this button to implement this on the line. And so this is the idea of manufacturing intelligence, is to create this feedback loop, but also to still have the data record that engineers can go dive into and feel comfortable about the changes that are being made. So this is what manufacturing intelligence will be, but we're at a nascent stage in the development of this. This is a new field, and so I want to talk you through what it is today, because something that when you're building something that's intelligent, you don't just like start with a brain. You actually have to teach it, and you have to teach it with a lot of data, and that takes time. And so I'd love to walk you through what we do in the creation of essentially where our brain is in terms of development today, what capabilities it has, and kind of how that capability could grow over time as an example of essentially where this industry could go in general. And so I start there by kind of outlining essentially where data technologies have been over time. And so I mentioned a little bit that there's this idea of manufacturing analytics, and that's not like super old, but it's not super new. And then there's some old stuff over there. And what's very interesting is that I've been on Apple lines that still have paper-based tracking. That's a technology from like probably before the 1970s, where they still track cosmetic defects by drawing little scratch images on little maps of the product on pieces of paper. Most manufacturing sites have manufacturing execution systems. These are the systems that essentially that pass-fail result is going to, but it's only recording pass-fail. The MES system is mostly about, is this phone okay to ship? Like, can I ship it? Has it passed everything? And how many phones can I build with the inventory I have left? That was the purpose of that system. So a very valuable system, but it was built in the 90s, and there hasn't been much since, and really manufacturing analytics hasn't taken off. So if that's the case, like moving towards manufacturing intelligence is kind of the next thing, but it has to prove that it's valuable enough to be adopted, because everything since the 90s hasn't been adopted. Ultimately, though, key point is that manufacturing is not figured out. So that no matter whose name is on a product, or who built the product, who the contract manufacturer was, it is hard, and nobody's that good at it. I think people kind of get this idea like, oh, Apple must be great at manufacturing. They build such beautiful products. Or like Samsung built so many products. Like, they must be awesome. And the thing is that, like, yeah, they're pretty good, but it's still hard, and they still make lots of mistakes. Those products don't come out on time. iPhone X, AirPods, like the list could go on. And then also, they have like major failures in the field, like Samsung Galaxy Note 7. So like their processes aren't catching major problems, some of which could be safety related, and they don't result in on-time shipment. And actually, the lack of on-time shipment is a major revenue killer for a new product. If you think about like an iPhone X, if they don't have enough, I don't know when they go on sale, but like they don't have enough the first weekend, they're actually losing sales because they're supply constrained. And that's massive amounts of money for a product like that. So it needs to be better, and nobody's got it figured out. It's not figured out. So what people want, and we want as a phone company, us collectively, is we want to know the moment a defective unit has been on the line so that we can send an engineer to go fix it, and then we don't have to make any more that are like that. What's very interesting about the way that new product development is done today is that you essentially like build stuff on the line, and you kind of cross your fingers and hope that your engineer is going to be at the right place at the right time to find the defects. And if they're not, that you have test stations in place that will phase gate and be like, oh, this one's bad, so we can like maybe go get some failure analysis and learnings about what we should change about our design. And this process is really long. It could take 18 months to get a new product out, 2 years to get a product out, and you could build tens of thousands of units and never get shipped during that process. And if you have to, so I don't know how many of you are software engineers in here, but if you're software engineers, this is like every time you push the compile button, it costs you like $1.5 million, and you really only get to push it 3 times. So that's what the world that hardware engineers work in, and honestly, it could be even worse in semiconductor space. And so there aren't tools to actually make this process better, and data is an opportunity in that space. And if it was easier to get better data today, we would already have it. But it's not easy because of the way that these manufacturing sites are set up. So essentially the data right now is put in the filing cabinet, like the proverbial digital filing cabinet. And what we really need is we need to have access to that. And to get access, it means we need to trust the cloud. And right now manufacturers do not trust the cloud. It's very interesting because major cloud providers don't trust their own clouds to store their own pre-production product data, which I think is silly because their clouds are secure. We put our financial data in the cloud, like the cloud is secure. And so what we really need is a way to essentially change the perception from it being an insecure place to put data to it is secure. It's actually more secure than your system that's never receiving any Windows updates and has known exploits that are located on your site. The second one is that, in general, factory internet is notoriously slow and unreliable. Internet in China is getting better, but in a lot of these manufacturing sites are in rural areas. And the internet being fast is kind of a novelty. That's not like a requirement. It's hard to see that coming from Silicon Valley, where like I need like all this internet to be able to use my social media, but this is just not the way. And so essentially you have to build a product that works in that environment, and your engineers need to understand like that internet's not going to be up all the time, so this product needs to work without internet, and then when the internet comes back it needs to be able to like figure it out and get its data out up into the cloud. And so it has to be designed for that environment from the ground up, because it's a different design than if you're building it in Silicon Valley and to work in Silicon Valley where you have really fast, reliable internet. And then the last one is that collecting data just having a bunch of data isn't necessarily useful. And that's kind of been one of the key obstacles to manufacturing analytics, in my humble opinion, is because just having a dashboard, that's great, okay, it's data, but what do I do with it? There's a lot of it, and I'm an engineer, I'm getting barraged with data already, so having algorithms that can highlight for you what you should look at would be really useful, and that's kind of where manufacturing intelligence starts. So there's 2 steps. First step is we need to collect actionable data, so not data for data's sake, but useful data that actually tells us stuff. And for that we need sensors. And those would be any kinds of sensors. Here I have pictured a camera as a simple kind of sensor. And then we need to know when failures happen, because if we can pinpoint when they happen, we can go and we can fix them before they create more problems and cost us more money and cause delays. And so I want to describe our example of manufacturing intelligence system where we have hardware that enables us to collect actionable data, in this case photographs. Photographs are a great kind of measurement to take because you don't need to know what you're looking for when you take the photo, but you can find lots of useful stuff in there, missing parts, parts unassembled correctly, burrs or cosmetic defects, workmanship issues, design issues. Again, you don't need to know what you're looking for, so when you go back you can see, oh, that was assembled wrong, or oh, I designed this bad, like those parts are interfering. And you can see that in the image, but you didn't have to know in advance those things were going to go wrong. And then we have software that works to tell our customers when failures happen, so they can go to the line and fix it right then and there. So I want to move over to